These are the full solutions to the 2010 AP Chemistry exam. You should go to the AP Chemistry website at collegeboard.com to download and print a copy of the exam to use with this video. 1A. The reaction for AgBr dissolving in water is AgBr solid going to Ag plus and Br minus. Ksp is the equilibrium constant for this reaction, so Ksp equals the Ag plus concentration multiplied by the Br minus concentration, and according to the problem, this has the value of 5.0 times 10 to the minus 13. AgBr is a solid, so its concentration does not enter Ksp. B. We set up the ICE table. We start with no Ag plus and Br minus initially. The changes are plus x and plus x. Applying the changes to the initials, we get x and x. Putting these back into Ksp, we get x squared equals 5.0 times 10 to the minus 13. Solving for x gives Ag plus and Br minus concentration equals 7.1 times 10 to the minus 7 molar. C. It would have been the same. As long as we have a saturated solution of AgBr, it always has the same Ag plus and Br minus concentrations no matter what volume it has. D. A saturated solution of AgBr has Ag plus and Br minus concentrations equals 7.1 times 10 to the minus 7 molar. This is the maximum concentration of Ag plus and Br minus. If AgBr dissolves completely, the Ag plus and Br minus concentrations must be less than 7.1 times 10 to the minus 7 molar. We calculate the molar mass of AgBr. The number of moles of AgBr in 5.0 grams is given by the mass divided by the molar mass. If the AgBr dissolves completely, the number of moles of Ag plus and Br minus are both equal to this. If the volume is Y liters, then the Ag plus concentration is 0.0266 mole divided by Y, and this must be less than 7.1 times 10 to the minus 7. We solve for Y, and we see that it must be greater than 37,000 liters. E. To determine if a precipitate will form, we compare the value of Q against K. We need the concentrations of Ag plus and Br minus, but these are not the same as those given in the problem because the total volume has changed when the solutions are mixed together. we calculate the number of moles of Ag plus and Br minus by multiplying the volume in liters by its concentration. The total volume is the sum of the two. So we divide the number of moles of Ag plus and Br minus by the total volume to get the initial concentrations of Ag plus and Br minus. Q is a product of them equals 1.0 times 10 to the minus 8. This is larger than KSP, so a precipitate will form. F1. The reaction occurs when I minus displaces Br minus to form AgI, so the balanced equation is AgBr solid plus I minus going to AgI solid plus Br minus. Two, if this reaction occurs, it must be because AgI is less soluble than AgBr, so that AgI will precipitate preferentially over AgBr. Therefore, Ksp for AgI must be smaller than AgBr. Two A. The graph shows the temperature of the solution during the experiment. At the beginning, T is 25.0 degrees C. At the end, when the temperature reaches its final value, T is 21.8 degrees C. So the temperature change is minus 3.2 degrees. B. The solution cools, so the reaction must be endothermic because it withdraws heat from the solution. C. Heat equals mass times the specific heat capacity times the temperature change. The total mass of the solution is 91.95 grams of water plus 5.13 grams of urea equals 97.08 grams. One, Q of the solution is the mass times the specific heat capacity of the solution given by the problem times the temperature change from A, and that's minus 1305 joules. Q of the reaction is a negative of this because whichever heat is lost by the solution goes into the reaction. So Q of the urea dissolving equals plus 1.3 times 10 to the third joules. 2. To compute the delta H per mole of reaction, we need the number of moles of urea. The molar mass of urea is 4 times 1.0 gram for H, plus 2 times 14.0 grams for N, plus 12.0 gram for C, plus 16.0 gram for O, equals 60.0 grams per mole. The number of moles of urea is the mass divided by the molar mass. Delta H equals the heat of reaction from above divided by the number of moles equals to 15 kilojoules per mole. D. The relationship among delta G, delta H, and delta S is delta G0 equals delta H0 minus T times delta S0. Putting in the numbers from the table, we can calculate delta S0. Be careful about the units for S. It comes out to be 70.1 joules per mole per K. E. If the measured delta H is 11% less than 14.0 kilojoules per mole, we get 12.5 kilojoules per mole. F. Cold urea would have decreased the temperature of the solution more than urea at the same temperature of the solution. So the calculated delta H would have been higher since Q solution equals mass times specific heat capacity times delta T. (3a) 1. The number of moles of Cl- is the volume in liters multiplied by its molarity. 2. The number of moles of Cl2 is related to the number of moles of Cl- by stoichiometry. According to the balanced equation, every 4 moles of Cl minus produces 2 moles of Cl2. So the number of moles of Cl2 is 3.125 times 10 to the minus 3. The ideal gas law gives volume if N, T, and P are known. T is 22 degrees C, but we need to change this to absolute temperature. P is given by the problem. So putting these into the ideal gas law gives V equals 0.0797 liter. B. According to the rate law, the rate of a reaction is equal to the rate constant K multiplied by the concentration of each reactant to some power. We will let the orders of Cl minus, MnO4 minus, and H plus be A, B, and C. 1. Using experiments 1 and 2, we get rate 2 divided by rate 1 equals concentration of Cl minus in trial 2 to power A divided by the concentration of Cl minus in trial 1 to power A. The other two concentrations are the same in both experiments and they cancel out. On the left, we get approximately 9. On the right, 3 to the power A. So A is 2. 2. Using experiments 2 and 3, we get rate 2 divided by rate 3 equals the MnO4 minus concentration in trial 2 divided by its concentration in trial 3 to the power B. On the left, we get approximately 2. On the right, we get 2 to the power B, so B is 1. C. 1. Putting the orders into the rate law, and given that the order in H plus is 3, we get rate equals to K times the concentration of Cl minus squared times the concentration of MnO4 minus times the concentration of H plus cubed. 2. To calculate K, we can use any of the 3 experiments. We will use 1. Putting in the rate from experiment 1 and the concentrations of the 3 reactants, we can calculate K. But watch out for the units of K. K equals 1.93 times 10 to the minus 3 molar to the minus 5 second to the minus 1. D. No. If this was an elementary step, it would require 2 molecules of Cl minus, 1 molecule of MnO4 minus, and 3 molecules of H plus to collide with each other at the same time to lead to a successful reaction. The collision of 6 species at the same time would be extremely rare. 4a, 1. Because potassium hydroxide and nitric acid both dissociate completely, the reaction would be OH minus from potassium hydroxide plus H plus from nitric acid going to H2O. 2. At the equivalence point, the same number of moles of OH minus has been added to H plus. Since the product is H2O, the pH would be neutral at the equivalence point. But past the equivalence point, the solution should be acidic because more than enough nitric acid has been added, so the indicator should show yellow. B1. The combustion of any hydrocarbon is its reaction with oxygen to give CO2 and H2O. To balance this equation, we need 3 CO2 on the right and 4 H2O. This makes 10O on the right, which needs 5 O2 on the left. 2. The solution should be acidic because when CO2 is dissolved in water, it makes carbonic acid. 1. The decomposition of hydrogen peroxide gives oxygen gas. The balanced equation is H2O2 going to H2O plus 1/2 O2. 2. In H2O2, the oxidation state of H is +1, so the oxidation state of O should be -1. 5a. In C2H2, there is a triple bond, so the Lewis structure should look like this. There is a triple bond between the two carbons, and a single bond from each carbon to hydrogen. B. C2H2 should have the shortest CC bond because it is a triple bond. C. Here we will use lines to represent bonded electron pairs. The structure of ethanol is this. Around the first carbon, there are 3 bonded electron domains and no lone pair, so the geometry should be trigonal-planar. Around the second carbon, there are 4 bonded electron domains, so the geometry should be tetrahedral. D. That statement would be false because when the liquid evaporates into a gas, only the intermolecular interactions would be affected, not the chemical bond. E. CH3CH3 and C2H2 should be nonpolar because their molecular geometries are completely symmetric. F. We draw the structures of both molecules. In ethanol, we have an OH bond. In ethanethiol, we have a SH bond. O is more electronegative than S, so the OH bond is more polar than the SH bond, and ethanol should be more soluble in a polar solvent like water. Six A. Metallic zinc is in the fourth row. It should have the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. When zinc is ionized, the two electrons come from the 4s orbital. So the electronic configuration of zinc 2 plus should be 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, but 4s0. B. Zinc 2 plus should have higher ionization energy than zinc because it is already doubly ionized, and each successive ionization energy is higher than the previous one. C. In this reaction, Al on the reactant side goes to Al3 plus on the product side. The oxidation state of Al is 0. For Al3 plus, it is plus 3. So Al is oxidized. D. When the cell operates, Al go to Al3 plus in the left half cell and zinc 2 plus go to zinc in the right half cell. So positive charges build up on the left and they decrease on the right. Ions in the salt bridge must move to balance this out. So NO3 minus should move to the left half cell and Na plus should move into the right. E. Zinc 2 plus is reduced and Al is oxidized. So the cell potential is the reduction potential for zinc 2 plus going to zinc minus the reduction potential for Al3 plus going to Al. You can look up the reduction half potentials from the table. The overall cell potential is plus 0.90 volt. F. Because the overall cell potential is positive, the reaction is spontaneous, so delta G should be negative. G. The cell potential changes with the concentrations of the ions. The relationship is given by the Nernst equation. Q is the reaction quotient. For this reaction, it is the initial concentration of Al3 plus squared divided by the initial concentration of zinc 2 plus cubed. For the concentrations given, Q is less than 1. The log of Q is therefore negative. With the minus sign in front, the second term is positive because RT over NF is never negative, so this increases E.